Good morning. In the last lecture, I discussed subfields and extension fields. I defined the minimal polynomial of an element beta in an extension field gfq to the m over a subfield gfq. We proved some properties of the minimal polynomial, including that it exists, it's unique, and it's irreducible over gfq. In today's lecture, we'll develop a formula for computing minimal polynomials. I'll begin by recalling the definition of a minimal polynomial. Recall that gfq to the m is an extension field of gfq, and gfq is a subfield of gfq to the m. Alpha is an arbitrary element in the extension field. Then the minimal polynomial of alpha over gfq is the monic polynomial over gfq of smallest degree that has alpha as a root. We proved that the minimal polynomial of alpha exists, is unique, is irreducible over gfq, and has degree at most m. In this lecture, we'll develop a formula for computing minimal polynomials. The strategy will be to describe completely the set of all roots of the minimal polynomial of alpha over gfq. And since every root corresponds to a linear factor, we can then recover the minimal polynomial by multiplying together the linear factors corresponding to the roots of the minimal polynomial. We'll show that the roots of the minimal polynomial of alpha are precisely the so-called conjugates of alpha over gfq. Our main theorem will use the following result. The result characterizes elements alpha in the extension field gfq to the m that are also elements in the subfield gfq. So let alpha be in gfq to the m. Then alpha belongs to gfq if and only if alpha to the q equals alpha. Here's the proof. Recall from the corollary to Fermat's little theorem that beta to the q equals beta for all elements beta in gfq. And hence the q elements in gfq are all roots of the polynomial y to the q minus y. We're considering this degree q polynomial to have coefficients in gfq. Now, since the degree q polynomial can't have more than q roots in a field, because recall that each root of the polynomial corresponds to a linear factor, and the degree q polynomial can't have more than q linear factors. Hence, the q elements beta in gfq are precisely the set of all roots of this polynomial. It follows that alpha to the q equals alpha if and only if alpha is in gfq. I'll next define the notion of conjugates of alpha. Let alpha be in gfq to the m, and let t be the smallest positive integer such that alpha to the power q to the t equals alpha. Note that we have a double exponent here. So this is q to the power t, not q times t. I'll note that t is well defined. This is because by the corollary to Fermat's little theorem, we know that alpha q to the m equals alpha. And so there exists a positive integer t such that alpha q to the t equals alpha. Hence, there must be a smallest such positive integer t. And in fact, t is at most equal to m. I'll next define the set of conjugates of alpha with respect to gfq. This is a set denoted C of alpha that you get by starting with alpha and repeatedly raising this element to the power q. So you get alpha to the q squared, all the way up to alpha q to the t minus 1. And I've stopped at this element since the next element in the list will be alpha q to the t, which equals alpha, the first element in the list. Observe that the T elements in the set of conjugates of alpha are distinct. This is because if these two conjugates were equal to each other, where let's say I is less than j, then we have this expression, and by the Frosch's dream, we can factor out a power q to the I to get this expression. Note that q is a power of the characteristic of the field gfq to the m. Hence, this term must equal 0. And alpha to the power q to the power j minus I equals alpha. But j minus I is positive and less than t. And so this equation contradicts the minimality of the integer t. Hence, the set of conjugates of alpha has size exactly t. I'm now ready to state the main theorem of this lecture, which is our formula for computing minimal polynomials. So let alpha be an element in the extension field gfq to the m. Then the minimal polynomial of alpha over gfq is m of y, which is the product of linear factors y minus beta, as beta ranges over all conjugates of alpha. In other words, m of y equals y minus alpha times y minus alpha to the q times y minus alpha q squared times y minus alpha q to the t minus 1, where t is the smallest positive integer, such that alpha q to the t equals alpha. Note that the degree of m is t, which is the size of the set C of alpha. To prove this theorem, I need to show you that the polynomial m defined here is monic, has alpha as a root, has coefficients in gfq, and among all such polynomials is the one of smallest degree. So let's prove the theorem. First, it's clear that m is monic, and that alpha is a root of m. The latter being because y minus alpha is a factor of m. Next, we'll prove that any non-zero polynomial over gfq that has alpha as a root must have degree at least t. So let f be a polynomial with coefficients in gfq that's non-zero and has alpha as a root. Let's write f in summation notation as a polynomial of degree d, where the coefficients of f are in gfq. Evaluating f at alpha to the q, we get this summation. Since q is a power of the characteristic of gfq to the m, we can pull out the power q to get this expression. Now the sum is just f of alpha, which by definition is 0. And so f, evaluated at alpha to the q, equals 0. And so we see that alpha to the q is also a root of f. Repeating this argument, we see that all the conjugates of alpha are roots of f. Since there are t distinct conjugates, this means that f has at least t linear factors, and hence its degree is at least t. Finally, I'll prove that the coefficients of m belong to the field gfq. This is not obvious, because you'll note that the coefficients of each of the linear factors of m are in gfq to the m. And that's because the conjugates of alpha are elements of gfq to the m. So I need to argue that when you multiply out these linear factors, the coefficients of the resulting polynomial are in fact in gfq, not just in gfq to the m. I'll do this by showing that the coefficients mi of the polynomial m satisfy the equation mi to the power q equals mi. And so by a theorem we proved earlier, each mi is in gfq. Okay, let's do that. So I'll write down the polynomial m in summation notation, where each coefficient mi belongs to gfq to the m. We want to prove that each mi is in fact in gfq. So let me start by raising this polynomial to the power q. I'll do this in two ways. By raising this expression for m to the power q, and raising this expression for m to the power q. The first expression to the power q is this product. By the Frosch's dream, I can write y minus beta to the q as y to the q minus beta to the q. I'll next note that as beta ranges over all conjugates of alpha, beta to the q also ranges over all conjugates of alpha. And so I can simply change beta to the q by beta without changing the polynomial. And now you see that this product is m evaluated at y to the q, which is this expression. Here's a second way to raise m to the power q. I can then invoke the Frosch's dream to write the sum as this sum. So I've raised each term in the summation to the power q. Now the expression star and double star are two ways of expressing the polynomial m of y to the power q. And hence star equals double star. We can now compare coefficients of y to the iq in star and double star. And we see that mi to the power q equals mi. Hence, by the theorem we proved earlier, mi must belong to GFQ. So this proves that m has coefficients in GFQ and not just in GFQ to the m. We conclude that m is a monic polynomial of smallest degree over GFQ that has alpha as a root. And hence m is the minimal polynomial of alpha over GFQ. I'll next do an example of computing minimal polynomials. We'll consider the finite field gf2 to the 4, represented as polynomials over Z2, modulo this irreducible degree 4 polynomial. We've seen this field in previous lectures. Let's find the minimal polynomial of the element beta, which is x cubed plus x squared, over Z2. When calculating minimal polynomials by hand, it will be useful to have a generator alpha of the multiplicative group of gf2 to the 4, and also a table of powers of alpha. It turns out that alpha equals x is a generator of the multiplicative group of gf2 to the 4, as we saw in previous lectures. I've written down here a table of powers of alpha, beginning with the 0th power and ending with the 15th power. We see from this table that alpha indeed has order 15, and so is a generator of gf2 to the 4 star. You can also find this table in the handout section on Learn. So now we see from the table that beta is alpha to the 6th. By definition then, the conjugates of beta with respect to GF2 are the elements you get by repeatedly raising beta to the power 2. And so we have alpha to the 6th, which is beta, beta squared, which is alpha to the 12th, and alpha to the 12th squared, which is alpha to the 24, which I can write as alpha to the 24 minus 15, since alpha has order 15. So the third conjugate of beta is alpha to the 9th. The next conjugate is alpha to the 18, which is alpha cubed. And that's it, because alpha cubed squared is the first conjugate. So beta has 4 conjugates with respect to GF2. By our previous theorem, the minimal polynomial of beta over GF2 is given by this degree 4 polynomial, whose roots are the conjugates of beta. I'll first multiply the first and second linear factors together, and then the third and fourth linear factors together. I get this product of quadratic polynomials. To simplify the quadratic polynomials, I'll use the table of powers of alpha to simplify alpha 6 plus alpha 12 and alpha 9 plus alpha 3. So alpha 6th is alpha cubed plus alpha squared, and alpha 12th is alpha cubed plus alpha squared plus alpha plus 1. Their sum is alpha plus 1, which is alpha to the 4th. So the first quadratic can be written more compactly as y squared plus alpha 4y plus alpha cubed. Similarly, alpha to the 9th is alpha cubed plus alpha. So alpha 9 plus alpha cubed is just alpha. So the second quadratic is y squared plus alpha y plus alpha to the 12th. Now I'll multiply these two quadratic polynomials together. So y squared times y squared gives me y to the 4. I get cubic terms by multiplying this quadratic term with this linear term, and this linear term with this quadratic term. So this gives alpha plus alpha to the 4th times y cubed. Next, I get a quadratic term by multiplying this quadratic term with this constant term, multiplying the two linear terms together, and multiplying the constant term here with this quadratic term. So I get alpha 12 plus alpha 5 plus alpha cubed times y squared. And lastly, I get a linear term in y and a constant term. I'll then simplify these coefficients by using this table of powers of alpha. And as expected, the powers of alpha disappear, and the resulting polynomial has coefficients in the subfield GF2. So this degree 4 polynomial is a minimal polynomial of beta over GF2. Let's find the minimal polynomial of an element in GF2 to the 16. We saw a representation for this field in lecture V2e. The characteristic P is 2, and the extension degree n is 16. The polynomial f of x equals x to the 16 plus x to the 5th plus x cubed plus x squared plus 1 is irreducible over Z2. And so the set of polynomials of degree at most 15 over Z2, modulo f of x, is a finite field of order 2 to the 16. Let's now find the minimal polynomial over Z2 of the field element B, which is x squared plus x. We'll first find the conjugates of B with respect to GF2, and we'll do this by repeatedly squaring B. So the first conjugate is B itself. The second conjugate is B squared. The third conjugate is B to the 4th. The fourth conjugate is B to the 8. The fifth conjugate is B to the 16. And here are the next 11 conjugates of B. That's 16 conjugates in total, which is the maximum number of conjugates for an element in GF2 to the 16 over GF2. Indeed, the next conjugate is B itself. So the minimal polynomial of B over GF2 is this product of 16 linear factors, where the roots of the linear factors are the conjugates of B. This polynomial m of y has degree 16 in y. When expanded, its coefficients should be in GF2 and not in GF2 to the 16. In other words, the x's must disappear. Maple can do this tedious expansion for us. And we see that m of y is indeed a monic polynomial of degree 16 with coefficients in GF2. As a check, we can confirm that m is irreducible over GF2, and that b is indeed a root of m of y.
Next, in V6c, we'll use our knowledge of minimal polynomials to study the factorization of x to the n-1 over GFQ. This will be useful when we return back to cyclic codes. Because remember, that canonical generators of cyclic codes are the monic divisors of x to the n-1 over GFQ. So we'll start a two-part lecture on factoring x to the n-1 over GFQ in V6c. We'll see you then.